Thank you, and thank you for the invitation to speak here. Obviously, I would much rather be in person, but I think we would all much rather be in person. But I'm glad to be able to talk to some of you anyways in this format. So today I'm talking about explicit models of genus 1 curves. So here I don't mean anything technical by models. I mean literally, I want to look at lots of explicit equations. I mean, I'm not going to actually write down all the equations today, but I want to think about genus 1 curves very explicitly and think about applications of knowing such things. So what I'm going to do mostly is go through and talk about lots of different examples actually of applications that we have from understanding these models of genus 1 curves. So understanding ways to write down genus 1 curves explicitly and these various applications that have sort of come up through my mathematical life. So it's, as we add in little extra information, it turns out that we can do more and more. So for today, I mean, the motivation is, as always, for probably a lot of people here, is going to be that we're going to have an elliptic curve and we want to understand things about our elliptic curve. So this is going to be elliptic curve over a field, K. So most of the results I'll talk about work over any number field. Most of them I'll state over Q if that, but there will be modifications that make them make the results work over any number field. I just don't want to, put in the very complicated factors that might come in. So my elliptic curve, you can think of it if you want in, Weierstrass form. Here, short Weierstrass form. So A and B, say in Q or in K here, or, if we're talking about number field, you can think of just putting A and B into the ring of integers. Non-zero discriminant, of course. All right, to study this elliptic curve, we want to study its torsors. So this is just the idea that if you have a group, say, which E is, as you all know, in order to understand a group G, maybe the easiest thing to do is to understand the G actions on sets or spaces, representations. And here with an elliptic curve, well, we're going to understand its action on the simplest thing that we can, which is on curves. We can't look at linear spaces in this case, but we can think about curves and how to act on curves, and in particular, genus 1 curves that have a transitive E action. Okay, so I mean, I expect most people here are, obviously very familiar with elliptic curves and genus 1 curves, but I would just remind you that here a genus 1 curve does not necessarily have a rational point on it, but it does look, E torsor is going to be isomorphic to E over, say, an algebraic closure. Okay, so if we want to study E torsors, I mean, well, okay, we want to study genus 1 curves. We don't have to specify the E necessarily ahead of time. We just want to study genus 1 curves altogether. So there are lots of classical examples of genus 1 curves that people are probably very familiar with. Maybe the very first example that, if you ask a student to give you an example of a genus 1 curve, an algebraic geometry student, say, well, maybe they just give you Weierstrass equations, and that's fine. I mean, so elliptic curves, of course, are genus 1 curves. Maybe that is example 0. But if you ask them beyond that, they might say, okay, plane cubics, right? So nice, I'm just going to use Bjorn's standard notation here, nice plane cubics. So nice meaning smooth, projective, geometrically connected here. So some sort of plane cubic. And then, you use the genus formula and you find that these are genus 1, right? So, so here my curve is sitting inside P2. Okay. And then maybe the second example that someone might come up with, even if they've never thought about this very much, is they try to make cover, say, of P1, and it turns out that geometrically, if you take nice double covers, of P1 ramified at, say, 4 points. So you have 4 points over your P1, right? And there's 4 ramification points, and I can't really draw this, exactly to get the ramification points, but this is the real picture maybe. But the complex picture, of course, I mean, you do want things over the other parts. It's a bit hard to draw it in the real world. You use Riemann-Hurwitz, and you compute that this also has genus 1. Well, really, maybe I don't want 4 points. I really want a degree 4 subscheme here of P1. If I want to do things more arithmetically. Okay, and this gives me a curve that's giving me a double cover of P1 here. And okay, and so these things are things we can write down explicitly, right? So in the first case, you're just writing down a cubic in 3 variables. And in the second case, well, how do we write this down? We describe this degree 4 subscheme explicitly. So you get a binary quartic form, degree 4 polynomial in 2 variables, homogeneous polynomial in 2 variables. So maybe let's call it F here. Okay, so we can write down something like this. And then we write, say, z squared equals f of xy. To be a little bit careful because we're working in, say, a weighted projective space. But we can write these things down very explicitly, these kind of double covers. Okay, so we have equations for all of these things. Okay, and then maybe the third example that I'll mention right now is you could take the intersection of 2 quadrics. So maybe a beginning student wouldn't come up with this example, but this is a question I would ask on an oral exam for our generals here, our prelim exams. So you take the intersection of 2 quadrics, and you can use a junction, say, to compute that the genus of such a thing, well, nice, again, would be genus 1. And in this case, right, your curve sits inside P3 here. Okay, so these are all very classical examples of genus 1 curves that people many years ago knew about. There are other examples. For example, you can put genus 1 curve into P4 in very nice ways. So this is perhaps this was probably known even more classically than this, just how to do it or how to write down equations for that, but it's sort of done more systematically in the work of Eisenbud and Buchsbaum. And there's more work about it due to Fisher, and you basically take a Pfaffian, 4x4 Pfaffians of a 5x5 matrix of linear forms in 5 variables and intersect those things. So it's not a complete intersection, but it does give you equations, quadratic equations, for what a genus 1 curve in P4 would look like, for example. We don't have great equations great ways to describe genus 1 curves in higher PNs in general. But of course, there are ways to do it for specific examples or for some subsets of genus 1 curves. But for today, these examples sort of will give us a good idea of the applications that I want to talk about. Okay, so the first application I want to mention is about splitting Brauer classes. So for each of these applications, I just want to, sort of mention what the problem is and why understanding things about genus 1 curves allows us to answer this question, at least in some cases. So here the question is the following. I take a field, right, which I set in the beginning. In this case, I might as well take an infinite field because it doesn't matter if I take a finite field, then the Brauer group is trivial, and so this question will not be very interesting. So if you want, you can take an infinite field. Okay, and then I want to think about an element of the Brauer group of this field. And the question then, the overall arching question is what fields split this Brauer class? So in other words, I have this Brauer class and I want to ask, and so if this isn't something that people have thought about, everyone here has thought about a lot, right? I'm thinking of a Brauer class maybe as represented by an Azimuth algebra or a central simple algebra. So something that looks like a sort of twisted matrix algebra, okay? Where when I go up to some field extension, say I go up to the algebraic closure, then I know, for example, that this algebra really does look like a matrix algebra. It is isomorphic to a matrix algebra, but over the base field that I'm working in, it might not look like that. It, it's a twisted version of that. And so you don't really have to go up all the way to algebraic closure. You could ask, okay, when can I go up? To what fields can I go up where this thing does actually look isomorphic to the matrix algebra? Or in terms of the Brauer group, I'm asking, I have a Brauer element. I'm asking how far up do I have to go so that that Brauer element becomes trivial? Okay, so that's a very basic question about just Brauer groups, and like an element of Brauer group is like, where do I have to go to like trivialize things? And the word that we use is splitting the Brauer class, is where it gets trivialized. So if you want to ask about fields, okay, well maybe if I want to make this a more geometric question, I can ask, okay, what varieties maybe split alpha, and maybe here I just want to think about irreducible varieties to make my life a little bit easier. Okay, and to think about that, it's a little bit easier maybe to think about this all geometrically. So from this alpha, from this Brauer class, I can make something geometric, which is a Severi Brauer variety, or Brauer Severi variety. Never clear which way to put the order of those words, those names. Okay, so I have a Severi Brauer variety associated to it. Let me call it B for right now, which over the algebraic closure is just basically a projective space. So one way to see that such a thing will be around is that this element alpha here, this comes from an element of H1, the alpha specifically, say, comes from an element of H1 of PGLN, say, for some n. And so associated to elements of H1 PGLN here, Galois cohomology, I mean, these things look like, or elements of here can be represented by sort of twists of Pn minus 1, since PGLN acts on Pn minus 1. Here's the automorphism group of Pn minus 1. Okay, so things here, these alphas, we can think of them sort of geometrically as there's an associated thing. I mean, this isn't a unique thing, but there's an associated Severi Brauer variety, which is some sort of variety that looks like Pn minus 1 over the algebraic closure, but it's not that necessarily over the base field. Okay, so it's a twisted version of a projective space. So then this question becomes, does there exist some variety, what's called X, for which X can you write down a rational map? So we want to ask which x's give a rational map to our Severi Brauer variety B. That's what this question about splitting becomes when we turn into geometry. Okay, and so this application, maybe the answer, well, there's lots of things do, but the answer that we're interested in here is that many genus 1 curves do. They split an arbitrary Brauer class, say. And this is, work of lots of people, but I worked on this with Johan de Jong, for example, in various cases. And the idea here, the way it's an application of what I've described already, is we want to twist the above constructions. So we describe these various maps from genus 1 curves to various projective spaces, just P1, P2, and P3. And so we're going to twist these up to get sort of genus 1 curves that map to my Severi Brauer variety B. So remember, I should think of B as a twisted version of projective space. And so in these cases where, n is small, 2, 3, 4, and we do 5 as well, we take these constructions and you sort of twist them up and then show that it actually gives you well-defined curves over your base field. So that's the basic idea. So in the very first case with the plane cubics, the idea is, well, if you have a Brauer variety of dimension 2, that looks like a twisted P2, right? And well, there's an anti-canonical bundle around on that twisted P2, which if it weren't twisted would look like O of 3. And so plane cubics are sections of O of 3. So all I do is take sections of the anti-canonical bundle on this twisted P2. Okay, so it's a twisted version of what we were doing before, is I knew how to make genus 1 curves that map to these projective spaces, and I just sort of twist this up. And I mean, you have to check everything works, but it does in these cases. And so the point is that understanding those examples, just understand how to construct genus 1 curves that map to projective spaces actually allowed us to answer this question. And maybe I'll just mention right now that people have continued to work on this question, and Ben Antio and Asher have very recently, I mean, just a few weeks ago, have shown a lot more cases of this, meaning, for many other sort of ends here, bigger ends, they've been able to do this. They use other techniques as well, but this was a start at least. So that's just one application that I wanted to mention that I thought was a fun problem. And actually, especially for the graduate students, I should say that this was something that I knew nothing about, this problem, but actually understanding something about genus 1 curves when, presented with this problem, Johan told me about this problem, and I'm like, oh, wait, we know these constructions, and then we can do something here. So it was a bit of a side venture for me at first. Okay, and actually in studying this, what actually becomes relevant if you want to ask, which genus 1 curves split the Brauer class, not just that some do, you start thinking about, okay, well, what were the constructions actually doing? And the constructions that we described actually are more than just random constructions that happen to give you genus 1 curves. They're actually moduli problems. So actually, we're doing things very precisely here. These classical examples, with the right equivalence relations, you get precise moduli problems. So what I mean is here, so if I take binary cortex, okay, and actually I should be careful here, and I don't want all of them. I want ones that sort of turn out nicely. So I'll just call them non-degenerate for right now. There's a discriminant associated to that. You want that to not vanish, for example, or you can think of the, I want binary cortex such that you actually make a genus 1 curve, a nice genus 1 curve when you write down that double cover. Okay, so you don't want two of the roots to come together, for example. So if I put the right equivalence relation here, and I'll mention what that is in a moment, then actually I get a bijection here with the information of nice genus 1 curves. Let's call them C, and maps to P1 in this way as double covers. Well, what are maps to P1 in this way? So I could write, maybe I can write here. So it'd be, C to P1, that's a double cover here. But what is that geometrically? I mean, I can keep around this information of the map to P1, but maybe it's a little bit better to just keep around the information of, well, this is actually, I mean, what is a map to Pn in general? Well, usually it's given by sections of a line bundle, and here it's degree 2 line bundles. Okay, so some linear system here, but actually here it's a complete linear system. So all I have to do is remember a degree 2 line bundle, and that gives me exactly these maps. Okay. And that turns out to be exactly the information that you get from a binary quartic. Is exactly one, from one of these things, you're getting a curve and a degree 2 line bundle. So, I mean, you're getting this line bundle from pulling back O of 1 on this P1 to the curve, right? And so that tells you sort of, how to go in this direction. From a binary quartic, we were able to make this double cover with equations, and then you get these two pieces of information. And you can go back, because if I have these two pieces of information, I can write down what the map from the curve to the P1 is, and it is a 2-to-1 map, and I can look at where it's ramified, and that gives me my binary quartic. Okay, so you actually get this bijection, and in fact, it's not just a bijection. Really, it's a deeper isomorphism between this sort of stack quotient, if you want, and some moduli space over here. So this is something very precise, actually, if you're very careful about what this equivalence relation is and what you mean, of course, by isomorphisms on this side. And so I said, well, you have to be careful about that. More or less, this equivalence relation is just linear transformations, okay? And the reason I said you have to be careful about it, I'm not writing down exactly what that is you do have to be a little bit careful about like taking not just say GL2, but you want a GM that acts on your binary cortex as well, and then understanding, exactly what group you want. More or less, the product of that at modded out by things that are repetitive works. But there's a little bit of care you need to place there. But you can keep doing this. I mean, for the case of plane cubics, you can also do this. So again, let's say non-degenerate. So what I mean is things that will give nice plane cubics. So plane means 3 variables, so ternary cubics up to the appropriate group action, which again is more or less linear transformations. And you get exactly the same information. So you get your curve C, and here this is going to be degree 3 line bundle. And that's because that's what's coming out of your map to P2. You have a curve, your genus 1 curve with a map to P2, and if you pull back O of 1, that gives you a degree 3 line bundle. Here. So it turns out that this is exactly the right information. You can write this all down as moduli problems. And you can keep doing this with the other cases as well. So you write down, this actual isomorphism between the two sides. Okay. And when you do that, you can push this a little bit further, right? You don't have to just, now these aren't just random constructions of genus 1 curves that I happen to have. Now I actually understand the set exactly of genus 1 curves over my field with associated line bundles. Okay, so I understand this much more precisely, and that means we can start doing things with with this side if I want to understand this side, because I do have this bijection here. Okay, so to start talking about that, I do need to introduce the Selmar group. So I just want to, talk a little bit. This is a bit of an aside, maybe review for most people here, but maybe not everybody. So I want to just mention it. Okay, so my e-torsors, my genus 1 curves that are torsors for a specific elliptic curve here are going to be classified by the Gallo cohomology group H1 of E here. Okay, and if you a priori didn't know that you wanted to study e-torsors, you could maybe make some analogy with the class groups. So if instead of E, you were thinking about the group GM, right? Then here maybe you want to think about H1 of GM, and this is the Picard group. Or if if my K or my base here is say the ring of integers of a global field, then H1 OK of GM is going to be my ideal class group, and that's something that we're all very interested in. Presumably, as at least number theorists are usually very interested in ideal class groups of say number fields. Okay, so I want to think about this H1KE, and it's well, here I'm working over a field, but over any regular ring, this is going to be a torsion group. So I want to understand its p torsion, say. Okay, and to understand the p torsion of this, well, maybe I'll use the Kummer sequence. So use the Kummer sequence. So again, there's some analogy with the GM version where you study the Kummer sequence there, but here with elliptic curves, I get this Kummer sequence. Okay, so I'm just taking multiplication by p on the elliptic curve, and then the p torsion is the kernel. Okay, so again, probably things everyone's thought about a lot. If I take the long exact sequence of cohomology, Gallo cohomology, and then simplify it up a little bit, I get the short exact sequence that tells me. So here you can take PW prime for today, but we don't have to, of course, for everything I'm saying. Okay. And so you get this short exact sequence after you simplify the long exact sequence from Gallo cohomology. Okay, so here, this guy is something we care about if we care about elliptic curves, because this more or less tells us about rational points on our elliptic curve, right? This is rational points, E of K, mod P E of K. So one of the many things that we care a lot about on elliptic curves are what are the rational points, or what do they look like here. Okay, and these are my e-torsors over here. Well, the sort of order P ones, right? And that's what we were saying we care about here. We want to study the P torsion of our group of e-torsors. And so we end up studying this thing in the middle, which, okay, are EP torsors, say. And there are lots of ways to describe this group. And one way to describe it that many people are familiar with, I think, are as P coverings, which are the genus 1 curves that have a map to E, which geometrically looks like multiplication by P. Okay, so maybe that means nothing to you if you haven't thought about these questions. But today I want to say that maybe you want to think about them a little bit differently. And they actually, the set of things in here can be represented by pairs a genus 1 curve with a degree P divisor class. And I want to be a little bit careful here and say, so when I say divisor class, I mean a rational divisor class, which is not the same thing as having a rational divisor up to equivalence. So here, the divisor class, the class is defined over your base field, but not necessarily an individual representative of that divisor class. Okay, so it's not quite the same thing as what we were doing earlier with our line bundles, but it's close. Okay, and there's a small difference there, and the difference actually comes out to be a Brauer element essentially. That you have to understand here. Okay, but it's close, and so suddenly we're starting to think about things that are close to the moduli spaces that we just talked about. And if you take the sort of local version of this, so suddenly, okay, so take now K to be a global field. And then I want to take sort of the locally soluble version of this exact sequence. So what I mean is I want to ensure that everything in sight has local points everywhere. This again is probably an exact sequence people are somewhat familiar with, but I do want to mention it. Okay, so here I have the Selmar group, which basically means I'm taking these guys and I'm looking at locally soluble versions of them. Okay, and so this is something that we do care a lot about because of this exact sequence, really. Okay, so we sort of pass these locally soluble guys because, well, that makes our life a little bit easier, and it is something we can check. We can check if curves are locally soluble pretty easily and pretty concretely. And so often when we study questions about global points, like rational points, globally we simplify our lives by taking locally soluble things. Okay, and here this is Shah, the Tate-Shafarevich group, which again, I'm sure that people have seen before, but comes up in BSD. And here, so we're thinking about that e-torsors, well, okay, order P e-torsors that are locally soluble, but not globally soluble, actually. Okay, so that's what's coming up here. And so that's the locally soluble version of these guys. Okay, and so really, I mean, what I want to say is, well, the Selmar group is a subset of this, right? Because what I'm doing is taking everything in here and just imposing these extra conditions on them, these arithmetic conditions of local solubility. Okay, but actually there's something that sits in between here, which I'm going to write as, I'm just going to write it here for a moment as H1 of a theta group. So we can black box that for today. What the theta group is, it's a non-abelian group, so that this thing here is a pointed set. It's not actually a group. Okay, and it sits in between here. But what's going to be important for us is how to classify the things in here. So these are going to be genus 1 curves with degree P line bundles, or degree P divisors if you want. So here I had divisor classes, and here I'm actually having genuine divisors that are defined over my field. Okay, so at least hopefully you can believe that this is a subset here, because here I'm asking for my actual divisors to be defined over the base field, and here they don't, just the class has to be defined over the base field. And it happens, and you can prove this, that anything that's locally soluble, any divisor class that's locally soluble will actually have a divisor that's genuinely defined over the base field, so that this set here does sit in between these two. Okay, so, but the point is that these things are things we just talked about, right? These are the things that are coming up in the moduli problems that I just mentioned. These are the things where we have explicit models of these guys. Genus 1 curves with maps to projective space. Genus 1 curves with these degree P line bundles. So we were able to understand these things. So in trying to understand, so let's back up for a second. Our goal originally was, hey, maybe we want to understand e-torsors. Like, okay, and then maybe we want to understand that by understanding p-torsion there. And then, well, in order to get there, we want to study this thing, this group. And that leads us to trying to study this set here or the Selmar group here. Okay. And this is an old idea, a very old idea. This is not new at all in some ways. So maybe I'll mention this very old application. Maybe people won't like that I say it's old, but to me it's old in that it was well before my time, which is 2 descent and 3 descent, and using these ideas there. Or, higher descents actually, but explicitly, even, today, the computational models that we have to compute Selmar groups, to compute ranks of elliptic curves, goes through using binary cortex or ternary cubics to explicitly compute Selmar groups. So use things like binary cortex and ternary cubics to compute Selmar groups. And then that lets us compute ranks. So I'm sure people here, there are experts here in the audience that understand much better how all these algorithms work in Magma or in Sage, for example. But my understanding is they actually, are explicitly writing out binary cortex, for example, to do 2 descents. And then you have to understand exactly how many binary cortex you're getting up to equivalence. So you have to understand reduction and minimization of these binary cortex, for example. And you can do this for higher descents as well. It just gets much more complicated and harder. Okay, so this is an old idea. I mean, I think in the original Birch, Swinnerton and Dyer computations, they use these ideas. I mean, a lot of this is found in their original work to use exactly binary cortex to understand the Selmar group here. Okay, and so I mean this idea has been used, for many years. That if we want to understand, say, something about rational points or about SHA, the Selmar group is a good proxy for understanding these things. And in some ways, it's our only tool for understanding, say, rational points. And it gives you, an upper bound on rational points if we understand something about Selmar groups here. Okay, and so, and this thing, this thing that I didn't want to define precisely, this data, but that has to do with the moduli spaces that we're talking about. This is something that we can get our hands on. And so going from here, from this space that we understand the moduli space of, to the Selmar group is just imposing some local conditions, essentially, this local solubility. And that's something that, in general, we're able to do with things like sieves. Okay, and so that brings me to the next application. So this is newer, but instead of using these binary cortex and ternary cubics to compute Selmar groups, so we use, maybe I'll just copy this, in fact, use binary cubics and ternary cubics to count Selmar groups. And this also allows us to say something about ranks. So it lets us bound average ranks. So count Selmar groups on average, maybe I'll emphasize that part. Okay, and so let me just explain the idea here, which is that, well, we had this correspondence. Let me just use binary cortex as an example. Okay, up to their equivalence relation. We said, okay, well, these are equivalent to these genus 1 curves with line bundles. Okay, so we have some bijection here roughly. I'm non-degenerate, nice, putting in the correct adjectives to make everything work. Okay, and well, we can count. The idea is you can count these guys, count these. And you can use the geometry of numbers, turns out, to count these. And what I mean by counting, well, there are infinitely many of everything around. So of course, counting, you have to be a little bit careful here. So you need to order these two sides. Okay, so with some ordering, which here is usually done by the naive height of the elliptic curve that's around. So the Jacobian of the genus 1 curves on this side, and on the binary cortex, that turns out to be something about invariance. So you just understand the invariance of this binary cortex. So SL2, say, acts on your binary cortex, and the invariant ring is generated by two invariants, classically known as I and J of degrees 2 and 3. So those match up with the A and B from your y squared equals x cubed plus ax plus b of your Jacobian over here. So you order these things and then you count them. Okay. And well, actually, I didn't really want to count all binary cortex, right? I maybe only wanted, and I actually can't count all binary cortex so well. I do need to put in some local conditions, and so maybe I want locally soluble guys here, and that means I want locally soluble guys over here. Put some sieves in, and then, okay, so here my blue is, with the blue. Then this corresponds to, well, actually elliptic curves with two Selmar elements is what I'm actually getting now, if I'm looking at locally soluble versions of this. Okay, and what is the fiber here? If I just map down to elliptic curves, so this is just M11, say the moduli space of just elliptic curves down here, the fibers here look like two Selmar groups, right? I mean, I could have done this map without the blue if the fiber here would look like that H1 theta that I mentioned. And then the fibers, when I restrict to the locally soluble guys, are just the Selmar groups here. Okay, so by counting binary cortex, so by understanding this correspondence here, we're allowed to count the things over here and putting in the local conditions. That means we can really count Selmar elements, or in general, the Selmar sizes. Okay, we have an idea of how to count Selmar sizes. And this is on average because you count this and you count this and then you divide. Okay, that's the idea. And so this is, of course, I'm sure, again, many people here have seen this. This idea is used in the work of Bhargava and Shankar first. So this is about 2010, I'd say, to 2014. And the theorem is that the average size of the Selmar groups, so cell n of E, say, for E's ordered by height, by this naive height. Let's do so just over Q, but it does work over any number field. So this is, let's say, 3, 4, 7, 6 for n equals 2, 3, 4, 5. Okay. And this, the point is they're able to, make use of this idea here, but really they're exploiting these correspondences that we just talked about, these moduli problems, which in all these cases is somewhat classical, except for maybe the 5 case, which classical, I don't know, 1970s, I don't know if that counts as classical. But for 2, 3, 4, and 5, we describe these correspondences, and those are very, very classical ideas there. Okay, and then using that exact sequence, let me just repeat it here. Let's just use P. The exact sequence with Selmar groups involved and Shah. Well, really just the first part of this, just the fact that the rational points essentially sit inside the Selmar group. Then there's a corollary here that they get bounds on average rank of elliptic curves over Q. And the numbers are, well, from the 2 Selmar, you get 3 halves. So average rank is bounded by 3 halves. From 3 Selmar results, you get 7/6. And then from the 5 Selmar results, you get 0.885. the 0.885 requires some extra work. Okay, it doesn't. I mean, the 3/2 and 7/6 are things you can do. You can just compute with just this. You know what this average is, and then you're just asking basically what that means in terms of average rank instead of average size. So the average P rank of this group is how you get these numbers out. Okay, and then the average P rank here is going to be bounded by that as well. The 0.885 does require extra work, and I won't say anything more about what that is. Okay, so this has been work that probably many of you've heard of, but I want to mention further applications. So the fact that you know these sort of corollaries for many cases, or have average Selmar size for multiple cases, not just one, gives you an extra corollary. So application is to the Hasse principle for genus 1 curves, for certain models of genus 1 curves. And so again, let me emphasize that multiple Selmar averages, meaning I have it for more than one n for the same family of elliptic curves that give different rank bounds. Right, so the fact that we have these different bounds here, this actually says that there's lots of SHA. Okay, and let me just briefly explain why that shows that. So, and lots of SHA means there's a failure of the Hasse principle, right? The things in SHA were exactly what we said, were torsors that were locally soluble but not globally soluble. So that's exactly genus 1 curves that are going to be failing the Hasse principle. They're locally soluble but not globally soluble. They don't have a rational point globally. Okay, maybe I'll write that. So this is a failure of the Hasse principle. And so why is that? I mean, what do these numbers that I wrote down have anything to do with this? So, okay, so the point is that here in this green exact sequence that I've written here, right, for p equals 2, say, we're getting that we get an average rank of less than 3/2. So what that meant, right, as I was saying, is that says that, well, actually we're saying that this thing has to be essentially about average P rank of 3/2 here, and that's going to be split between this and this. Okay, but then the 3 Selmar says, well, actually, the average 3 Selmar is going to be, well, have rank sort of split with 7/6 here. It's split between this side and this side. The 7/6 has to be split on the two sides. Okay, and so the fact that 7/6 is a smaller number than 3/2 is really what's giving this to us. Okay, so the fact that these are two different numbers is going to give us something, which is that, well, I said that you're actually splitting, this thing is actually bounded, the rank of this is actually bounded by 7/6. That's what the 3 Selmar result gave us. But the 2 Selmar result said, well, actually, I have to split the 3/2 between here and here. And so what that means is, okay, if this is definitely less than 7/6, and then there's 3/2 that has to go into here and here, right? 3/2 is bigger than 7/6, so that means there's a lot of stuff that's going into there. That's it. That's all we're saying. Okay, so these numbers are really telling us, how big Selmar is, right? And so average rank, if we know it's actually smaller, that means there has to be a lot in the SHA side. Okay, so that's the idea, is just that you can sort of just look at this exact sequence and balance these out. Obviously, to actually prove things a little bit more precisely, you have to order things maybe a little bit differently. So maybe this is pretty much automatic if you're going to order with respect to the same height here, which is the height on elliptic curves. But if you want to order things, say, with respect to the coefficients of your models, that's a little bit different, and then you'd have to do some more work. Okay, so and that is done. So Mundell-Bargava has work, for example, in these cases, for exactly these cases, which show that for the models of genus 1 curves that we talked about for 2, 3, 4, so the binary quartic model, the ternary cubic model, and the intersection of 2 quadrics model, because we have this bound, this really good bound that comes out of the 5 Selmar thing, we show that there's lots of SHA in those cases. he proves that, basically there's a positive portion of those models that are going to fail the Hasse principle there. Okay, and he and I have some joint work in other cases as well that show some failure of the Hasse principle for the same reasons. Okay, so I've mentioned all these various applications that have to do with rational points on elliptic curves, but let me just say that if you actually want to think about integral points on elliptic curves, then you need to start thinking about moduli problems somewhat integrally. Okay. Well, maybe I don't mean that exactly precisely here, but the idea is, let me just do a quick example, is that, say, if you look at binary cortex, right? So we're thinking about these things, say, over Q or over a number field, okay, right? And we said, okay, these are corresponding to my C's and L's, degree 2 L's, okay? Well, maybe I can restrict to, say, integral binary cortex. And maybe I'll add in some more congruence conditions with some conditions. Okay, let me figure out what those conditions are precisely. Okay, so, well, let me write this first. Okay, so I want to try to, study this, but at the same time on this side, maybe I don't want all CLs. Maybe I just want to restrict to things that are actually the elliptic curve. So the torsor here is going to be the trivial torsor. And then that means that the line bundle here is just some O plus some point P, okay, where P is a point on my elliptic curve. Okay, so this is certainly some subset. I'm just restricting to the trivial torsors here. And then suddenly I'm getting basically elliptic curve and some points. And let me restrict further and actually ask for that point to be integral. Okay, well, I mean, I have to choose an integral model of my elliptic curve to make this make sense, but let's say I've done that. And so this thing that I'm writing here actually makes some sense. Okay, so I'm looking at integral points of my elliptic curve. And if you do all this very carefully, it turns out that you actually do understand these integral points here as certain integral binary cortex. So, I mean, what is the idea? The idea is, okay, this was all very rational, but if I start wanting to look at integral things here, I need to figure out what on this side will correspond correctly. And so one way to do this is say I want to look at integral points on this side of my elliptic curve, and these you can work out correspond to exactly certain kinds of integral binary cortex. So in particular, I'll just write, if you really want, for this correspondence, I want things that look like, oops, 6cx squared y squared plus 8d xy cubed plus ey to the fourth, where, well, c, d, and e are going to be integers, say. Let's just do this over z to make this a little bit easier, but so this is over z, and e is congruent to c squared mod 4. So something super explicit. I mean, it doesn't matter right now exactly what it is, but you can write down exactly what these things are. Okay. So, I mean, you can do this in many different directions, but this is one example of something you can do. In the sense that, like, if I restrict to just some kind of integral binary cortex, I can actually come up with correspondences on the other side, understand sort of the moduli problem this way. And there's an application here in this particular case. It's maybe a little surprising that comes out as something so simple, which is that you can get bounds on the number of integral points. So again, here, understanding this correspondence means that, well, if I want to study integral points on elliptic curves, that means I have to understand these things. And these are, again, some models of genus 1 curves. I mean, binary cortex, so I take, z squared equals this thing, and I get a genus 1 curve, and I understand those models. I understand how many of them there are. And so we count these things on this side, essentially. And this requires quoting some results from Diophantine approximation, but this is, maybe I'll just write a theorem with Alpaga-Levent, and myself, and you get bounds on the number of integral points for elliptic curves over, say, Q. Actually, we can do S integral points on elliptic curves over number fields in general. But the formula has become more complicated, of course. And a corollary of that is you get that the average number, or the second moment, or various moments on the number of integral points for elliptic curves over, say, Q, is bounded. So the point is, well, we can use understanding how many of these guys there are to bound the number of integral points on a given elliptic curve. And then once you can do that, once you can bound the number of integral points, we combine that with the previous work, actually these Selmar averages, to say something about averages and actually higher moments in this case. Okay. So, so the point is, if you keep pushing these things further, so I started with, okay, we're going to take constructions of genus 1 curves. You can get some applications out of that. If you understand that they're actually moduli problems, you can, push that a little further. And now I'm saying, okay, well, you can understand them integrally, and then you can push that even further to try to get applications in more integral ways, not just rational directions. And so I want to add one last, or maybe two last things about how to generalize this. So you can do generalizations. So you can get lots of other moduli problems like this, which give you more and more complicated genus 1 curve models with extra data around. But what they end up giving you are similar applications. With families of elliptic curves. So you can get these same applications, as I mentioned, these sort of average Selmar results and average ranks and families, things about the value of the Hasse principle, or things about integral points. You can do all of these things using these, slightly more complicated moduli problems that parameterize Selmar elements or elliptic curves with extra data. So genus 1 curves with some extra data that turns into elliptic curves in certain kinds of families with all of the same kind of data. So that's one direction you can go in this. But then the last application I want to mention has to do with multiple moduli interpretations. Okay, so we've been talking about, okay, you can have these moduli problems, but actually sometimes you're able to do a little bit more. And if you have one particular space, it turns out that it can be interpreted in 2 different ways, or more than 2 different ways. And sometimes that gives you interesting information. So I just want to give a quick example of this, which is this case of ternary cubics. So I'll just write ternary cubics here. Okay, so we already saw that these had to do with these CLs, where you have a degree 3 line bundle. Okay, so we already saw that. But it turns out that if you actually go through some of these other moduli problems that I'm mentioning here, and you work through some of the details of that, it turns out that these also look like, and here my arrows are not very precise. I mean, open sets on both sides because you need to, look at non-degenerate things. It turns out that you can actually interpret this same space as, well, genus 1 curves. Let's call them X here, just to differentiate from the other side. Degree 3 line bundles. Okay, this is sounding a lot similar when we call that LX. So it's degree 3 line bundle on that X. And a point on the Jacobian of X that's 2 torsion, actually a non-zero point. Okay. Oops, let me just squeeze this in here. Okay. So this seems really counterintuitive because it looks a lot like this side, except suddenly I've added information here. So it sounds totally crazy, actually, if you look at this for the first time, that these should actually look the same. This looks exactly the same, but suddenly I have more data on this side. Okay, so there's some work to be done here in understanding these moduli interpretations. But let me just say that this sort of recovers. Maybe I'll call it an application here. Oops, I was using purple, I think, for that. And this recovers the classical Hessian construction. And this interpretation actually gives you lots of other applications. So there's relations to dynamics and modular curves and Galois representations. So understanding in this way does give you further applications. So what the classical Hessian construction is if you take a plane cubic, okay, so you write that down as a cubic in 3 variables, then you write down the second partial derivative matrix. So that's a 3 by 3 matrix, the second partial derivatives. And each of those partial derivatives, second partials, is a linear form. So you take a determinant of that 3 by 3 matrix and you get another cubic. Okay, so this is a sort of standard example that in classical algebraic geometry, you take a plane cubic, you get another plane cubic. And actually that second plane cubic does come with a double cover of it, which turns out to be this 2 torsion point on its Jacobian. And so this understanding these moduli problems actually tells you that I can relate these things, this curve and this plane cubic, this curve with the line bundle, directly with its Hessian and that 2 torsion point. And we can get these out very explicitly. And by doing that, you can play a little bit more with these Hessian constructions and sort of pump out a little bit more information. I mean, a lot of this is very classical, and I mean, there are many people that have worked on this. So I don't want to claim too much here, but this is a phenomenon that you see by interpreting things with multiple moduli interpretations over and over, and you can recover different kinds of classical constructions this way and find some new ones too. Okay, so I will stop there, and hopefully I've given you some sense of the things you can do with these models and lots of different applications. Thank you for your attention.
Thank you very much. Are there questions? Oh yes, Samuel, you have a question?
Yes, I think there is another one also.
Yes, Valentine, please.
So I will be fast. I have 2 quick questions, more or less quick. So the first one is like, if you change your ordering of the curves, are you changing the average or not? For Selmar, for Shah?
You could. We don't know actually in some ways. We don't know how to prove things with other orderings in many cases. I mean, this is a problem in general in arithmetic statistics where we can often only prove things with certain orderings, and sometimes when you order things differently, you do get different answers. But there are very few examples that we can, actually order things. I mean, you could do stupid things like, of course, you can order your elliptic curves by rank, and of course, then what you're gonna for your average rank or something, or that won't work out so well. But I mean, for any sort of standard ordering, we can only prove things in certain cases, so we don't know. And this is
with Luca and Nicola, we are doing a project in which we are ordering things a little bit differently, and we have some results which are really in the same spirit. Probably, well, we will contact you. And I have another question, which is about your last application. I'm going to be really fast. So for the integral points, there are connection through the Fontaine equations directly to class numbers. So divisibility of class numbers, if you have, for example, the Somme-Bachet equation as integral points.
Yes.
You get some divisibility conditions there.
Yes.
Did you exploit that already, or?
So our bounds do not give better things, I think, for that. I mean, we checked, and at least following standard. I mean, we didn't push it too far, but sort of following the standard things. We have these bounds, and then we see what it gives. We didn't get better things. So we do get better bounds for integral points, but not for that stuff.
Perfect. Thank you very much.
Yep. Thanks.
Valentine.
Yeah, thanks, Wei, for your talk. I had a bit of a vague question. One of the questions Samuel already asked, but the other one was, since you mentioned the Hasse principle, can you also say something about weak approximation this way?
I don't think so. I don't think we get anything about weak approximation, but I don't think anyone's thought about it. I mean, I don't see an obvious way to do it, but that doesn't mean that you can't.
Okay. Yeah, just wondering. Thanks.
Yep.